Should
Okay, let's get started. Welcome back to CS2040S for another exciting week. It's been fun today seeing, seeing what you all expect from the future, looking at the discoveries that are going to change the world that you are going to graduate into in a couple of years. It seems like everyone here, or most of you, are very optimistic about AI. Lots of things about AI intelligence, Mahjong AI, certainly, no question. Can computers develop consciousness? Lots and lots of optimism that AI is going to change the world that we live in over the next couple of years. That's certainly interesting. An interesting thing is no one put anything down about self-driving cars, which a couple of years ago was the hot topic in AI. The hot thing people would have put down here as the big thing that was going to change life the next couple of years is self-driving cars. Maybe that doesn't show up today because everyone just assumes that now. Oh, it already exists. Why would we even talk about that? That won't be a big discovery. That's already been done. Or perhaps it's because here in Singapore, you don't own cars and hence this doesn't seem as big a deal to you. I don't know. But that doesn't show up anywhere on this list, while lots of other AI type things do, such as those robots doing all the work for you so you can stay home all day. Excellent plan. The other one, the interesting one that shows up a couple times on this list is things about aliens or space travel or living on Mars. I don't know, not sure about the next 5 years, but that's certainly an interesting set of questions for the future. And even two of you put something down about P equals NP, which would be our computer science theory major breakthrough, the biggest breakthrough you can imagine in computer science theory, I think. Anyways, as I said, fun to see what everyone is predicting for the next 5 years. In the random questions, I noticed, by the way, there was a question that came up on whether algorithms are political. And I think this is a fascinating question that I can't get into right now. There's not enough time. But there's certainly been a lot of discussion about to what extent algorithms are really neutral parties versus to what extent they can promulgate existing biases in society and so on. But anyways, I don't have time to get into that right now, but we can talk about it on the forum later if you're actually interested, since I think it really is a fascinating question. But I should get on with the main content of today. Today, we are talking about two interesting data structures, Heaps and UnionFind. And the way to think about today properly is that today is kind of an intermission. a break from graph algorithms. We have spent the last couple weeks talking about graphs and mostly shortest path algorithms. We're going to spend the next week or so talking about spanning trees and other sorts of graph algorithms. And today we have an intermission, a short break where we're going to talk about two tree-based data structures. In fact, we are recalling our tree-based roots from several weeks ago. And I will argue that this is a good thing, because one of the best ways to learn things is by seeing them every so often. This idea of punctuated repetition, that you see something, then you spend a little time away from it, and then you come back to it and repeat that a few times. This is the best way to learn something. So today we are coming back to talk about tree-based data structures again. Okay. Okay, so good. So this is the plan today. We're talking about, I said, these are sort of two completely separate data structures. Each will be about half of class. We'll spend about half of class talking about priority queues and about half of class talking about a UnionFind disjoint set data structure. Great. So to begin with, we're talking about heaps, which are a way to implement a priority queue. You remember from last week that a priority queue is just a way to maintain a set of prioritized objects, right? You can insert items with specific priorities, and the main operation you want is you can do an extract min operation. You can remove the object with the minimum valued priority or the maximum valued priority or whatever it may happen to be. Okay, and the sort of classic example of a priority queue is scheduling. If you want to, you might be keeping track of a set of tasks, a set of deadlines, and at any given time, you want to extract the thing with the earliest deadline first. So if there's something due on March 31st, you might want to work on that before you get around to washing your clothes. Just saying. Okay. So priority queue. We saw this last week in the context of Dijkstra's algorithm. We talked about it in terms of an abstract data type, right? Where you can insert, you can extract min, you can decrease key, you ask if it contains something, and so on. This was sort of the priority queue data type. You can, of course, have a minimum priority queue that looks for the minimum thing, or a maximum priority queue that does an extract max. I think for today's purposes, we're going to talk about maximums, not minimums, but hopefully you can do that translation yourself between the two of them. They're essentially the same thing. Okay, great. So we already know how to implement priority queues in several ways. The simplest way to implement a priority queue is probably just as a sorted array, right? I keep an array of things. Here they are. They're sorted in priority order. When I want to insert something, I just insert it anywhere in the array. I just insert it into the array and move everything over to make space for it. When I want to extract max, I just return the maximum thing in my array. Okay, great. Unfortunately, this will now take order n time to do inserts and order 1 time to do the extract max. You could, of course, imagine the opposite, an unsorted array where you just add objects to the end of the list. Insert is order 1. But now extract max, you have to search the whole array to try to find the maximum priority thing. It's order n. Okay. And of course, we talked about how you could use an AVL tree to implement you could use an AVL tree to implement your priority queue. In which case, an insert is just order log n to insert an object into a tree, and extract max is order log n to find the maximum element. Okay. Someone pointed out in the chat that if you have a sorted array, you could use binary search to search your array. Right, so you could, if you have a sorted array, you could use binary search to find the maximum element. But in fact, you don't need to use binary search because you know exactly where the maximum element is going to be. The maximum element is always going to be at the far right of the array. Okay, so in the sorted array case, binary search is unnecessary here. Okay. No, I mean for insert and delete. The problem with inserting and deleting in the sorted array is you have to move everything over. The problem is that what makes insert expensive is not finding the location, it's trying to move things to make room for them in the array. Okay, you can find the location using binary search, yes. Okay, so priority queue gets you order log n, and that's sort of the best we've seen. That's fine. And we also talked a little bit about some of the other operations in a priority queue. So you might want to ask if a certain thing is contained in your priority queue. You might want to implement decrease key, which means you take something and you change the priority of it, and so on. And in general, to implement these type of things, you're going to also need, in addition, some sort of hash table or some other way of finding some way to find the key in your AVL tree, for example, to figure out where this key went. Okay, great. And what we saw last time is, depending on how you implement your priority queue, you get different performance for Dijkstra's algorithm. Okay, great. So today I want to talk about another way to implement a priority queue. And there are two reasons we're talking about this. One is I think it's a particularly elegant data structure. It's sort of beautifully simple. The other reason we're talking about is that in practice, it actually is quite an efficient data structure, though we're going to see that asymptotically, we're not getting huge gains out of it. Okay, this is a case where the asymptotics don't fully reflect the performance we see in practice. Okay, we'll come back to that in a little bit. Okay, so we're going to implement a max priority queue. A max priority queue, or a max heap. So we're trying to be able to extract the maximum item from our priority queue. Right? We're maintaining a set of prioritized items. And the way we're going to do this is we're going to store the items in a tree with the biggest items at the root and the smallest items at the leaf. There's a continued message in chat about, isn't it possible to insert a new element into an array of size n in log n time using binary search? If you want to keep the array sorted, I don't know how to do that, because there is no space in your array. You need to make room for that item. And the only way to do that is to either move everything over or take an item out and put it somewhere else. But if you take it out and put it somewhere else, then it's not sorted anymore. Okay, okay. Sorry, it's hard to try to respond to questions and keep going at the same time. Let me talk about a heap sum. Okay, so a heap has two key properties to it. Okay? One of them is what we call the heap ordering property. What that means is that the priority of a parent should always be larger than the priority of a child. Okay, so you'll see the parent here is 20. And the children are 9 and 22, which are both less than 28. That's good. And here we have a parent of 22. Their children are 15 and 7, which are both less than 22. So that's also good. Okay. So in general, for every node in the tree, the parents should have priority greater than or equal to the priority of the children. You will also notice that this is not necessarily a binary search tree. Okay, so for example, 9 is bigger than both 5 and 3. If this were a binary search tree, 3 would have to be bigger than 9, right? That would be the binary search tree property. This does not satisfy the binary search tree property. Instead, it satisfies the heap property, the heap ordering property. Okay, so this is the first key property of a heap. Okay, second key property of a heap should be a complete binary tree where every level is full except for possibly the last. So what do I mean by every level? So you can think of your binary tree as taking place in levels, right? Here we go. Each of these is a level, and we want each one to be full. So 1 node here, 2 nodes here, 4 nodes here, and so on, up until the last level. And the last level, of course, may not necessarily be full. Okay. This is a pictorial argument of what I mean by a complete binary tree where every level is full except possibly the last, but hopefully it makes sense. And the other thing we want is for that last level, we want the nodes to be as far left as possible. Okay, we want to fill up this tree from left to right here. This is obviously an arbitrary choice. It could be from right to left as well, but it's going to be convenient for us to talk about from left to right. Sorry, left-handed people. Or maybe this is good for left-handed people. I don't know. Okay, so let's play our favorite game. This is the Is It a Heap game. So how about this? Indicate on your Zoom check in X, is it a heap? Yes or no? You get 5 seconds. You have to click quickly on these. 5, 4, 3, 2, 1. Oop. Yes, this is a heap. It satisfies the heap ordering property. It is a complete binary tree. Life is good. Let's keep going. Here's the next. Is it a heap? Yes or no? Again, we get 5 more seconds to vote. 5, 4, 3, 2, 1. No, this is not a heap. In particular, you will notice that this is not, the last level here has not been filled up from left to right. We have some holes in the middle. We don't want any holes in our heap. It does, I believe, satisfy the heap ordering property though, which is good. How about this? Is this a heap? Yes or no? Again, you have 5 seconds to click. Check or cross. 5, 4, 3, 2, 1. No, this is not a heap. This is not a heap because it does not satisfy the heap ordering property. Okay, 15 is bigger than 12, not a heap. Sorry, there's a question in the chat, I think, about why the previous one was not a heap. The previous one was not a heap because of these holes here in the middle. Nothing to do with duplicates. It has to do with the fact that it is missing some nodes here. That makes it not a complete binary tree with elements as far to the left as possible. Okay, but how about this one? Is it a heap? Here's a new one to talk about. This one's maybe trickier. But again, I will give you 5 seconds to guess. 5, 4, 3, get your guesses in. 2, 1. No, this is not a binary heap. Maybe I should add the word binary here. We are talking today about binary heaps. This is not a binary heap because it has 3 possible children here. There are k-way heaps and multi-way heaps you can talk about, which are interesting data structures in their own right. But today we are talking about binary heaps, so this does not satisfy our definition of a heap for today. Okay, there's a question in chat. Heap means it's balanced. Heap means it's not just balanced, it's stronger than balanced. It's a complete tree. Every layer is full. Okay, how about this one? Is this one a heap? This one I think should be easier. Again, check or cross. 5 seconds. 5, 4, 3, 2, 1. Over. No, this is not a heap. This is not a complete binary tree. Of note, it's missing a node here. If there were an extra node here, it would be a heap. Okay? So it is not a heap because it is not a complete binary tree where the last level is as full as possible. Okay, let's see. I think I have one more of these. How about this one? Is it a heap? Okay, here we go. 5, 4, 3, 2, 1. Yes, this is a heap. There's nothing in our definition of heap that prevents duplicates. If you go back and look at our heap ordering, it only requires that the parent is greater than or equal to the children. Okay, this is interesting, and you may notice this is actually, you may remember AVL trees, there was some complication you might run into with duplicate keys, right? Lots of duplicate keys in an AVL tree would cause trouble. You wouldn't be able to search it properly. In a heap, there is no problem with duplicate keys, okay? I see some comment in Python, some comment in the chat about Python and priority queues and duplicate items. And I will emphasize that different uses of heaps may or may not allow duplicates, obviously. It may turn out that certain priority queues don't want to allow duplicates or want certain behavior for duplicates. And that's totally fine also. That's part of the specification for your priority queue. But there is nothing inherent about a heap that makes duplicates a problem. If you choose not to allow duplicates, that's your own choice. Okay, good. So that is it for the Is It a Heap game. Hopefully everyone had fun on our game today and with fancy prizes. No, okay. Onwards. So that's a heap or a binary heap or a binary max heap. Okay. It's an implementation of a max priority queue, maintains a set of objects and so on. And the key 2 properties that you need are the heap ordering and the complete binary tree property. Okay, great. So we know what a heap is. Now the question becomes, is it any good? So, oops, I have to go to Archipelago. Let's warm up Archipelago now and see how it is doing today. Okay, let's see if that works. I have, in theory, just opened a question archipelago saying, what is the maximum height of a heap with n elements in it? And you'll notice that some of the answers include floors and ceilings, so please be precise today. There's a question in the chat, does this assume an total ordering of the content? And so yes, so for a heap, you need the elements to be ordered. We're talking about the priorities to be ordered. The keys themselves, no, but the priorities have to be ordered, right? Because we're talking about bigger and smaller priorities that only make sense in an ordered universe, okay? So we have to have ordered priorities for a priority queue or a heap to make sense. Okay, let's go on with this question, maximum height. The maximum height here turns out to be the floor of log n, okay? Which seems like it was an unpopular answer today, in fact. And honestly, when I'm given a question like this, how do I go about it? I actually tend to draw myself a few small examples to check it out. You can work it out theoretically, but I tend to draw myself a few small examples. And if you look at this, I drew you a nice little tree here to make this easy. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes in this tree. So the log of 10 is somewhere between 3 and 4, right? 2 to the third is 3, 2 to the 4 is 16. So it's somewhere between 3 and 4. The height of this is 0, 1, 2, 3. So you're going to think of the floor of log n as the, roughly the right answer. Then you have to double check. Is it the floor of log n or the floor of log n minus 1? You'd have to think through those cases to be sure. Someone in the chat says, forgot that height starts at 0. Yes, height starts at 0. Sorry. But the other way to think about this, of course, is that, well, our usual binary trees are something like log n. If it was completely full, you'd be getting exactly log n. And so it ends up being the floor because, well, it's just a little bit less than that. Okay, with, again, the height starting at 0. So what we know about a heap, what's great about a heap, is that it really is very, very close to exactly log n height, the absolute minimum height. Okay, so this is going to make a heap very efficient because there's no 4 log n or 2 log n or some constant times log n. It really is exactly height log n. Excuse me, without the big O notation causing, causing hidden constants to add things up. It's the absolute minimum height you can get. Okay, so given that, we want to look at the actual operations we want to do on a heap, right? We want to be able to insert items. We want to extract max, increase key, delete, decrease key, and delete. Let us go through these operations. First, we want to insert 25. Okay, so step 1, we should add a node with the key 20 with the priority 25. Well, where should we add this? I claim there is actually only exactly one spot in this tree that we can legally add this 25. Well, that's going to be right on down here. This is the only spot we can add while maintaining a valid complete binary tree. Okay, great. Let's do that. Let's add that there. So we add it as a leaf in the first spot available for it. Okay. We have maintained our binary tree property. That's good. Unfortunately, we have now violated our heap order property, right? Unfortunately, 25 is bigger than 3. That's a problem. Okay, so we need to fix the heap order property. And the way we're going to do that is we're just going to bubble up the 25 up the tree until we find the right place for it, right? So we compare 25 to 3. We discover that 25 is bigger than 3. And so we swap 25 and 3. We compare 25 and 9. We say 25 is bigger than 9. And so we swap 25 and 9. We then compare 25 to 28. We discover that 25 is less than 28. And so we leave things where they are. And so we are done. Okay. There's a question, how does it maintain a valid complete binary property when 3 only have 1 child? So the complete binary tree property is that all the levels should be full except the last. And in the last layer, the nodes should be as far to the left as possible. So this here, as we've drawn it, is a valid tree shape for a heap. Okay, great. Good. So this is how you do insert. I will leave you to do the inductive proof on your own, but you will see that once this is done, once we have finished this bubbling up process, we have again satisfied the heap order property and everything is good. Okay, great. So here's some pseudocode for bubble up if you like. It is nice and simple. Basically, we are just walking up the tree until we get to the root where v is null. We compare the priority to the priority of the parent. If the priority is bigger than the priority of parent, we do a swap. If we found the right place, then we are done. Otherwise, we keep walking up the tree. Okay, simple enough. So this is all we do for an insert. We add the key, and then we bubble up, and we are done. Okay. Good. And when we're done, we have maintained our two key properties. Our two invariants are maintained at the end of our insert. Okay, let's look at another operation. Let us look at the increase key operation. Let's imagine I have this key over here, 5, and I want to increase this to 25. Okay, well, how do I do that? Well, we already know how to do that, right? We already, in some sense, know how to do the bubble up procedure. So we change this 5 to a 25, and then we do this bubble up. We compare to the parent and we swap. We compare to the parent and we swap until we are done. Okay. There's a question in the chat about how do we implement the insert key? How do we implement this step way back here in the very beginning where I inserted 25 as the leaf here? Well, if you think about this as a tree, this is just a regular tree insert. We should keep track of where the next point in the tree we need to insert is, and we can handle this via tree insert. But we're going to come back to this also in a little bit. Okay, so let me postpone that for a few seconds. Okay. Where was I? Decrease key. Okay. Here is a decrease key. Imagine that we are sitting here we want to take this key of 28 and decrease its priority to 4. So we do that. We decrease it to 4. Again, we have maintained our tree shape property. It still looks like a heap. Unfortunately, we have violated the heap order property, so we're going to need to somehow do some movement. And again, the easiest thing to do in this case is a bubble down procedure. So in this case, we compare 4 to the value of our two children, 22 and 18, and we're going to swap the 4 with one of these two children. Okay. So here is the key question. Which way should we go? Should we bubble this down to the left? Should we bubble this down to the right? Or it does not matter. What do you think? Okay, I will give people 7 more seconds to put their answer in archipelago. 5, 4, 3, 2, 1, done. Okay, we want to bubble down to the left. Why do we want to bubble down to the left? Well, let's imagine what would happen if we bubbled down to the right. If we bubbled down to the right, we would have moved 18 up to the root. And that would not have solved our problem because 18 is less than 22. And so we would have violated the heap order property. So we want to bubble down to the left, putting the larger item up top. Okay, here we go. So bubble down compares moves the 22 down to the left. We then compare the 4 to the 5 and the 3. Again, we want to swap with the larger item, swap with the 5, compare the 4 to the 1 and the 2, and discover that we are done. Okay, great. So this is the bubble down procedure. It looks more complicated, but it's not. It's only because this is a verbose piece of pseudocode where we are looking at our left and our right priorities. We're figuring out which is the bigger of the two of them. And then we're going to swap with whichever one is larger and continue on down the tree. Okay, great. That's the bubble down procedure. So decrease key again is easy. We just update the value and bubble down. Once we're done, the heap order has been restored. And once again, we have never modified the complete binary tree property. Okay, great. How about delete? Okay, so delete's a little bit more, you have to be a little bit more careful because we can't just remove this node from the graph, from the tree without disrupting the property, the tree shape property. But you remember, whenever we delete from a tree, there's actually a standard trick we often use. Whenever we delete from a tree, it's convenient to swap the node with a leaf, which is easier to delete. We saw this before for binary trees. So same thing happens here, right? Let us swap the thing we want to delete with the last thing in our heap, right? Why do I want to swap with this one and not, for example, with this one over here? Well, if we swapped with the one over here on the left, and then we deleted it from the tree, we'd have a hole. It wouldn't be our complete binary tree with things that the leaves moved as far to the left as possible. We would be violating the tree order property, okay? So we want to swap it here with this item over here, which is the last item, which we can safely remove, okay? So that's what we do. We've swapped the item we want to delete there, like that. And once we've swapped it, we can just remove it, cut it off from the tree. It's done. We don't need it anymore, okay? Great. So now we've successfully deleted the item. Unfortunately, we now have a violation of the heap order property, but as usual, we know exactly how to fix violations in heap order property. We just do bubble ups and bubble downs as needed to solve the problem. So in this case, 2 is going to need to bubble down, right? So we compare 2 to the children 4 and 3, and we go and we do a bubble down procedure. Bubble down, and we are done, okay? Okay, great. Okay, good, so that's delete. How about extract max, okay? Extract max, you can just look at this as deleting the root, right? So we already know how to do that. We swap it with the item over here, and we bubble down, okay? There's a question of when do you consider bubble up versus bubble down? Well, it's going to depend on how the heap order property is violated. But if you look at what's happening on delete, by the way, for a delete operation, you are taking an item at a leaf and moving it up the tree somewhere. So at least if it's going to one of its ancestors, it's going to need to bubble down. If it's going over here, for example, then who knows what's going on, right? But basically, you can always tell how the heap order property is violated by looking at the parents and the child of the node in question. Okay. Okay, so extract max is doing a delete. Okay, good, and that's basically all we need to know for a heap, right? We have a bunch of operations: insert, extract max, increase key, decrease key, delete. They are all order log n. Okay. In fact, they're not order log n, they are floor of log n. They are basically exactly log n cost, which is wonderful. There's a question in the chat: is this stable? Okay, that's a fascinating question because you have to first decide what stable means in the context of a priority queue, where, yes, it's not clear exactly what stable means. You'd have to define a notion of stable, which you could do. But in fact, we'll come back to things being stable in a second when we talk about sorting, okay? Okay, so a natural question at this point is we already knew how to build a priority queue with cost order log n using an AVL tree. Why would I prefer a heap versus an AVL tree? As I said at the beginning, they are the same asymptotic cost for operations, right? Everything is still order log n. Okay, good. On the other hand, in general, it's a faster real cost because you don't have the constant factors, right? This floor of log n does tend to be better than order log n. It tends to be a little bit simpler than an AVL tree, no rotations. This is one of the reasons it reduces all those constant factors. And in practice, it also gets slightly better concurrency, which, again, we're not talking about in this class. So in general, if what you want is a priority queue, a heap tends to be a faster implementation than an AVL tree, even though they have the same asymptotic cost. Okay. There's a question in the chat about what about delete? How do you search for the key? And you're right, just like when we talked about the AVL tree, we're assuming there's some extrinsic way to find the thing that you want to do increase key, decrease key, or delete on. You can't search for something in a priority queue. That operation doesn't exist. So the assumption is that you have you have a hash table, or that tells you where to find something, or perhaps if you're using it to implement Dijkstra's algorithm, each node might have a pointer into the priority queue to show you where the item is. There's some external way to find the node that you're interested in. Okay, that's something that you need both for the AVL tree and the heap implementation of a priority queue, in fact. Okay, good. So I was saying that a heap is faster than that the heaps in general are faster than AVL trees, even if you implement them as trees. But it turns out we can do something even better than that. We don't need to implement our heap as a tree. We can actually implement our heap using an array, okay, which is a kind of amazing thing. So here's the idea. We're going to store our tree in an array. Okay, we're not going to have a whole bunch of nodes and pointers running around. We are just going to have an array. We're going to map each node in our complete binary tree into a slot in the array. Okay, and luckily this is pretty easy to do. So the root, where does the root go? Let's map the root to slot 0. Okay, great. There's a comment in chat, oh no, this is quadratic probing. I wish it were, because I'd love if this tied into quadratic probing somehow, but I don't think it does. But that would be wonderful if I could just tie everything together that way. Okay, so the root goes to slot 0. That's great. Then let's look at the next level of our tree. Okay, the next level of our tree is going to map to the next 2 slots in our array. So 10 and 17 go to slots 1 and 2. The next 4 are going to go to the next 4 slots in our array. Here we go, 8, 4, 6, and 5. And the last one is going to go at the end. So we are just going to map our tree into our array slot by slot. Okay, not quadratic probing, some other type. Okay, maybe. So good. This is a nice and simple mapping, and it turns out it's pretty easy to translate back and forth between the array index and the location in the tree. Okay, so let's just look, for example, how this is going to work now. Let's imagine I want to insert 15 into this array. Into my priority queue here. This is a max heap that I'm trying to maintain. So as usual, where do I put the item when I insert it? I put it down here. Okay. There was a question: how do you know where to put the item when you insert it? Well, if you've stored your tree as an array, the correct place to put the item is exactly the first empty slot you find, the last slot in the array. So you find the last slot, you find the last full slot, increment it by 1, and that is going to be the new location for your new node. It is immediate to find where to put the new item. It is an order 1 cost. Just drop in your new node where it belongs. That's easy enough. Okay. Now we need to do our bubble up procedure. Okay. There's a comment. Remember to expand the array. Yes, you will need to be using the shrinking and doubling as per the amortized analysis to maintain the proper size of your array. Of course. So to do that, we have to compare 15 to its parent. How do we do that? Its parent is over here. Okay, so we need to compare these two and see which is bigger and do a swap. In fact, 15 is bigger than 8, so we do the swap. That's good. We keep going. We compare this to its parent. We compare 15 and 10. 15 is bigger, we swap. Then we compare again to its parent over here, and again, it's done. Okay. So this is the usual bubble up procedure. Okay. Now, if you want to implement this efficiently, it'd be really nice if we could easily calculate things like left and right and parent without having to do complicated math on these indices. Okay. Now, you can think about this for a bit, and I bet you can figure it out yourself. But in the interest of time, I will give away the secret that if you want to find the left child of a node in slot X, you just have to look at slot 2x plus 1. So I want to find the left child of something in slot 1. Where am I going to find it? I'm going to find it in slot 3. Where am I going to find the right child? In slot 4. So 2x plus 1 and 2x plus 2, they give you the left and the right children. Okay. Someone in the chat pointed out something about out of bounds errors. Yes, be careful of out of bounds errors in a real array, of course. Okay, so left and right are 2x plus 1 and 2x plus 2. Given that, I bet you can reverse engineer how you find the parent. Well, the parent is just going to be the floor of roughly x over 2. In fact, the floor of x minus 1 over 2. So if I want to find the floor of something in slot 4, for example, 4 minus 1 is 3. 3 divided by 2 is 1.5. Round down gives you 1. I find the parent over here in slot 1. Okay? So to calculate left and right children or parents is just a single simple calculation, essentially multiplying, dividing by 2, and taking the proper +1, -1 offsets. Okay, great. So here is a, okay, so this is, before we get there, so this is how you do it in a heap. One natural question, as I said, we can do this with a heap. How about an AVL tree? Do you think we could do this same thing with an AVL tree? Can we store our AVL tree in an array? Okay, because we're gonna talk in a sec about how it's faster to store things in an array like this, because it makes all the memory lookups faster. We don't have to chase pointers around. Everything is stored consecutively in memory. In general, scanning arrays is much faster than scanning lists. So can we store our AVL tree in an array? If so, how would you do it? And if not, why not? And it's worth thinking for a sec of sort of what happens when you want to store an AVL tree in an array. I'll give you a sec to think about that and type in a few words into Archipelago. Okay, I see a bunch of answers here where a lot of people, I think, have the right idea that you are going to run into problems when you store your AVL tree in an array, okay? I mean, you can, of course, take your tree. I mean, imagine this is an AVL tree. Did I even draw it correctly? I don't know, but imagine this is an AVL tree. And for whatever reason, I need to do a rotation in order to fix this AVL tree, in order to, it's out of balance. You see it's out of balance. And now I need to do some rotations to fix it, right? Okay, so now I go to do some rotations. Let's see what happens if I do a right rotate on 15. If I do a right rotate on 15, you'll notice I need to change all of these items here, need to be updated to do that rotation, right? So it used to be in our old world that a rotation in an AVL tree was an order 1 cost operation. Now, if I want to do a rotation, I need to move all the stuff in the subtree around if I want to keep the proper structure, right? If I want to keep the proper mapping between the array and the tree, I'm going to need to move everything, and it's going to be super expensive. So right, rotation around the root would be a linear cost operation. It might be order n cost to rotate, to do a rotation around the root, okay? So unfortunately, rotations become a lot more expensive because we don't have this nice these nice properties, and so it's going to be expensive. One of the beautiful things about a heap is we don't have to do these sorts of rotations. We do these simple bubble up and bubble downs, and those we can do efficiently, okay? There's a second problem, of course, that because you have all these gaps in the tree, see all these gaps in your tree, depending on how, that's not a gap, these are the gaps. Because you have these gaps in the tree, you might actually need a lot more space. So there's a question of how big would your array have to be? And so, for example, let's imagine that your AVL tree were height 2 log n. It won't actually be 2 log n, it'll be 1.44 log n. But just for the sake of argument, let's imagine your AVL tree were height 2 log n. What that would mean is that you would need n squared space in your array to store it. Okay. Or again, if it's 1.44 log n, it'll be n to the 1.44. Okay, so you're going to need super linear space to store your tree now, and that's also unfortunate. Okay, so again, there are ways you can do this, there are optimizations you can make, but in general, it's going to be quite hard because of expensive rotations and because you need too much space. Okay, great. Good. So that's how you store a tree in an array. And again, as I said, this is great for heaps because it means everything runs super fast. Everything is now being stored directly in an array. Operations are just log n array accesses. It is roughly as fast as you can get for a priority queue, or for this type of priority queue anyways. And so that's excellent. Okay. Okay. So next question. One of the things that a priority queue can be used for is to implement a sorting algorithm, right? If I have a priority queue, I can clearly build a sorting algorithm. And here's one we're going to build using a heap called heap sort. Let's look at that. Okay. So we start out with an unsorted list, and we go through 2 steps. In the first step, we translate our unsorted list into a heap. Okay. And in the second step, we take our heap and we produce a sorted list from it. So we're using a heap as an intermediate state in some sense between unsorted lists and sorted lists. Okay, great. Good. I'm going to start out by talking about step 2, which I think is the easier step. Let's start. Usually we start with 1, but let's start with 2 because we like binary. I don't know. So for step 2, we already have a heap, and we want to convert that heap into a sorted list. Okay. So here's our heap, here's the array representation of our heap, here is the tree representation of our heap, and we want to take our heap and we want to build a sorted list. I claim this is quite simple and straightforward. You already know how to do this. All we have to do is we extract the maximum item from our heap, we do an extract max, and we already know exactly the last item in our heap. So let's do that. We extract max, we take it out, and we update our array and our tree. Everything is good. We've found the maximum item in our heap, the maximum item in our sorted list. But now here's the question, where should I put this maximum item that I found? I've just found the last item in my sorted list, so I should put it at the end of my array, right? Hey, look at this. I just happen to have a free spot sitting here at the end of my array. What luck is that? How lucky. Let's just put that item there. So let's put the item we just found at the end of the array that we already have. That's good enough, right? Now let's repeat. Again, extract the max. In this case, the maximum is 17. After we do the extract, we're going to have an extra space here at the end, and we can just put that item here at the end where it goes. Okay? And we keep going. We just keep extracting the maximum item and putting it in the new free space that we have just generated. Extract and put the end, extract and put the end, extract and put the end, and so on. And if we keep doing this, eventually we end up with an empty heap and a perfect sorted list. Okay, so that's pretty neat, right? So we have a nice simple algorithm for turning our heap into a sorted list using no extra space. Maybe you have like 1 integer of extra space to store or one item's worth of space to store the item while you're swapping it or something. But essentially a nearly perfect space efficient heap. Okay, good. So here's the algorithm. Again, you can write it in like 2 lines of code. It's great. You're just going through every item from the end to the beginning, extract the maximum item, and drop it at the end of just at the end of your heap. Good. So what's the running time for converting our heap into a sorted array? Okay. We're going to do this quickly, since I think this should be easy. Let me go back to the slide in case you want to see the pseudocode. Here's the pseudocode. Okay, great. You have 5 more seconds. 5, 4, 3, 2, 1, go. Order n log n. Okay, and of course, it's not surprising that it's order n log n because we have each of these extract max operations that runs in order log n time, and it is a loop that runs for n steps, and so the whole cost is order n log n. Okay, and this shouldn't be all that surprising in some sense because sorting feels like it takes, all our other sorting algorithms take n log n time. It turns out that all comparison-based sorting algorithms take n log n time. So it's going to take n log n time to do this step. Great. Okay, so we now know how to do step 2. Let us go back and do step 1 again. Okay, now we have to take an unsorted list and turn it into a heap. Let's look at that step. Okay, so the first, there's sort of an obvious solution to this. The obvious solution to this is just go through our entire list and insert the items one at a time into our heap. Okay. That's the easiest thing to do. Take each item, insert it into our heap, and we're done. If you do it that way, it's going to run in order n log n time. So it goes. Okay. Let me give you a different algorithm for inserting things into a heap. Let me give you a version 2 heapify algorithm for turning our unsorted list into a heap. Okay. Here's the key idea. The key idea is recursion. We're going to start with some already existing thing that has the right shape. It's a complete tree with all the levels full except the last as far to the left as possible. But it doesn't satisfy the heap order property. And we want to ensure this whole thing, when we're done, satisfies the heap order property. Okay. Now, if we go through and try to just sort of randomly bubble things around, it might be a problem. But if we do things carefully in the right order, it's going to work. And so the key idea here is recursion. Let's think about what's the base case of our recursion. Our base case is that every leaf, here are all our leaves, every leaf is already a heap. That's good, right? We already, in fact, solved basically half our problem. All the leaves are already heaps. Okay, so now what we want to do is we want to go through, and the inductive step is going to be to take a node that is not a proper heap. Both of its children inductively already are proper heaps, and we want to fix it. Okay, and of course, the way we fix it when we have one node that's wrong and 2 children that are proper heaps, we already know exactly how to fix this type of thing. We just do a bubble down procedure, right? We compare the 8 to the 3, we bubble it down. So we're comparing 8 and 3, we're bubbling it down the tree, we've moved the 8 up, and now this little triangle over here is a proper heap. Now we do the same thing over here. Again, both the children are proper heaps, do a bubble down, it's going to be right. Let's keep going. Again, both the children inductively are already proper heaps. We do a bubble down, we end up with a heap. Notice that the key property of bubble down that we know is that if both children are heaps and we bubble down, the result's a good heap. If we don't know the children are already heaps and we do bubble down, who knows what'll happen? But if we know the children are both proper heaps, then everything works. And again, we do a bubble down on 6 now, and we are done. Okay, great. And so again, this leads to a nice sort of 1 or 2 lines of code where you just iterate through from the end of your array to the beginning and doing a bubble down. Okay. And so if you think about very carefully what's happening when you do this, the first, whole bunch of calls, we're looking at leaves. A bubble down on a leaf doesn't do anything. Okay. From then on, we have the invariant that whenever we look at a node, both of its children are already going to be proper heaps, and so the bubble down works. And by the time we get to here, the invariant says both of the children are heaps, and so it works, and so on. And so we just keep iterating through the list until we have finished. Okay, good. So naively, it might look like the cost of this is order n log n. Bubble down generally has cost order log n. There are n elements here. It looks like this should be order n log n. But it turns out that if we're careful, we will get something better. Because think about it, the cost of doing a bubble down operation is the height of the tree, right? It's not always log n, it's the height of the current node in the tree. Okay? And here's a nice observation. N over 2 of the nodes are leaves, right? So the bubble down operation for all of these leaves is going to be, well, order 1 for each of them, right? Then we have a whole bunch of things up here, the things that are height 1, whose cost is going to be something like 1 or 2. And then the next level up is going to be, cost 3, and so on. Okay. Let me see if I can say this more clearly than I just said it. So most of the nodes already have small height. And so the cost of building a heap is we're going to have at most n over 2 things of height 0, n over 4 things of height 1, n over 8 things of height 2, n over 16 things of height 3, and only one thing actually has to spend log n. Okay, so to figure out the proper cost, we have to sum up this summation. Okay, so then we have to pull out our discrete math textbook and look at the summation from 0 to log n of, well, we're doing sort of n over 2 to the h. N over 2 to the h is going to be the number of nodes of height h, right? This is, let's see, this is the number of nodes that we have at height h. Great. This is the height of the tree and hence the cost of the bubble down operation. And so this is the total cost, okay? And I will leave you and your discrete math textbook to check this out for yourself. But if you solve this summation, you will discover that it is order n, okay? That the cost of this is order n. So in fact, it is better than order n log n. It is in fact only order n to turn to build this heap, okay? Great. So this is kind of surprising, in fact. We've taken an unsorted list and we've turned it into a heap in only order n time, which is kind of amazing. And again, it gives you this remarkably simple piece of code. Okay, great. So what do we know from all of this? We know that we can start with an unsorted list. We can build a heap in order n time. We can turn it into a sorted list in order n log n time. And we have a wonderful new sorting algorithm called heap sort that now sorts in order n log n time. Okay. This is a n log n worst case time. Unlike, say, quicksort, this gives you an order n log n worst case time algorithm that needs only n space plus maybe some little o of 1. You know, maybe there's some little o of 1, you know, extra space you need, but not much at all. Sorry, I was trying to draw a plus o of 1, a little bit of extra space, but really this is about as minimal as you can get space-wise. In practice, this turns out to be faster than merge sort because of the efficient memory use. It turns out to be a little slower than quicksort most of the time. Probably not always, but for whatever reason, it turns out in practice to usually be a little slower than quicksort, but it's deterministic. So if you need, you know, if your algorithm runs too slowly and your spaceship blows up as a result, I would use heap sort and not quicksort, because even if quicksort fails 1 out of every 10,000 times, maybe you don't want to take that risk blowing up your spaceship. Okay, it is unstable. Someone asked about the stability of a heap earlier, and I wasn't sure exactly what you meant by the stability of a heap. It's something you can actually define. But once we use it for sorting, you can show that it will end up, the heap sort will end up being unstable. And here is a great exercise. Why don't you come up with an example where you can prove that heap sort is unstable? Okay. I also mentioned earlier, by the way, that this is a two-way heap. You can, of course, have a ternary three-way heap or a multi-way heap. What I've read, at least, I haven't run the experiment myself, is that three-way heap sort is a little faster than two-way heap sort, but it tends to get a little slower around four-way and five-way. But I don't know for sure. I'd love if you ran the experiment and told me which is the fastest heap sort. Okay, good. I think that's all I have to say about priority queues and binary heaps and heap sort. So we will at this point take a 5-minute break and come back to talk about the second half of class. Okay, let's get started again. We have part 2 of our class to do. We are moving on to a separate data structure. Okay, for now, you can put aside what we've just done talking about heaps and move on to a new problem. Okay, as I said, this is a 2-part class with sort of 2 separate things. I think you might have been hearing about mazes recently. I'm not sure why. I have this hint that you've been thinking about mazes recently. So along the way, one sort of maze problem you might ask is there any route in our maze from Y to Z? Okay, and luckily we already know how to find that. If I just want to know, does there exist a route from Y to Z? I'm not talking about shortest paths here today. I just want to know, does there exist any route from Y to Z? We can use BFS or DFS, and we finish in order E plus V time. Wonderful. Okay. Let's think about a different version of the problem. Let's imagine that I don't want to ask just one query. Okay. Instead, I would like to pre-process the maze. I'd like to do a bunch of upfront work. And once I'm done, I would then like to be able to ask a lot of these connectivity queries. So I might ask if those points are connected, and I might ask if these points are connected, and I might ask if these points are connected, and so on. There might be a whole series of these connectivity queries. Okay, and perhaps instead of having to spend a whole BFS or DFS every single time, I can do this more efficiently. And in fact, let me ask you just that question. How do you think you could pre-process this maze in order to answer queries faster? Okay, what do you think? So there's a question over in Archipelago. Why don't you go and see if you can think of an answer to this? What's the fastest? What would you do? What would you like to do to pre-process the maze first? And then how would you go about answering queries quickly? What kind and how is the question is asked in chat. The question is how to pre-process this maze so that you can answer lots of queries more efficiently than having to do a BFS or a DFS for every single is connected query. Notice on your problem set, we didn't ask you to handle lots of different queries like this. You're allowed to basically spend every query doing whatever you want. Here we're saying you should optimize so that you can do a lot of queries on the same maze. Comment in the chat, everything is a graph. It's true, I said this is an intermission from thinking about graphs, but well, it's only a little bit of intermission from thinking about graphs. Okay, I'm gonna go on in a sec. I see a bunch of people have, well, a bunch of people have the right idea, a bunch of people seem confused, and a bunch of people are being a little bit cheeky and saying this and noticing this is a class on UnionFind and suggesting we use the UnionFind algorithm. Okay. But really, before we even get to that, we want to pre-process the maze in some way that we can quickly, in order one time even, decide if 2 points are connected. That means we need some way of annotating the maze to specify what's connected to what. And if you think about this for a little bit more, and as I said, a bunch of people essentially gave this answer, what you really want to do is divide your maze up into connected components, right? Of course, I haven't actually, my maze is not actually accurate this way, but I've tried to draw in, hypothetically what the connected components of your maze are. Maybe all of these places are connected, and maybe all of these in C are connected, and maybe all of these in F are connected, but there are no doors or gates between these sections of the maze for whatever. Okay, so you can imagine going through and doing a whole series and doing a big BFS or DFS to explore the entire maze. And for each connected component, you're just going to label each location with the name of that connected component. Okay, and now when I want to ask if two things are connected, it's very easy. I just check, oh, so this location is at B, this location is at C, drat, those clearly aren't connected. Or this location's at D, this location's at D, they are connected. So now I can pre-process in order V plus E time. That's just one breadth first search or depth first search covering the whole maze. And then I can answer is connected queries in order one time. So this is a very common thing we often want to do. We want to pre-process, save some information, and then use that to solve other problems. Another relevant factor, by the way, is how much information you have to store. You notice here we're storing about order n information if n is somehow the number of rooms in this maze. Okay, that's the amount of information we're having to store during our pre-processing, which is always an important parameter here. Okay, now let's think about the one step harder version of this. So that's if you just want to look at a static maze. But what if, say, you can destroy walls in your maze? I gather you're familiar with this type of problem too. Imagine that I want to pre-process the graph so that I can answer queries, and also I can destroy walls in my maze using maybe your superpowers, and I still want to be able to answer these type of is connected queries. I still want to know I still want to know whether two things are connected even after I destroy walls. So obviously I'm going to have to do some work when I destroy walls to update my connectivity data structure, right? So for example, here in this case, I'm going along and I am destroying the wall between B and F here. I destroy a wall that connects those and makes them part of the same connected component. And now I need to update my data structure as a result. Okay, okay, good. And so now let's, this is all well and good. This is the problem we want to solve. This is the dynamic maze problem. Destroy walls, we're going to think of as a union operation because it's combining two sets of things together. And we're going to actually model this all as a graph of connected components because, like you just said, we tend to model everything as a graph. So I can stop drawing maze pictures that look like this and have confusing colors on them and just switch to a nice simple representation like this, where each connected component is now represented by a node. Okay, great. And for every, so there are two types of operations we support here. Union lets us essentially draw an edge. It connects two things together. We have destroyed the wall between E and F here, okay? And now that's a single connected component of our graph, okay? And another union operation, we combine I and G, and another union operation combines D and E, and another union operation combines B and A. And now, once I've done a whole bunch of union operations, I might want to ask, are two things connected? And that operation we're going to call a find operation for historical reasons. The find operation is asking, is there a path connecting these two objects? So we have G over here and I over here, and the find, and they are connected. This find is saying we have not G and D, these two things here. We're asking, is there a path between G and D? And the answer is no, false, okay? We might ask if there's a path between D and F, and between D and F, there is a path. They are connected, so it returns true. And we can go on and do some more union operations and some more union operations and some more union operations. And eventually we now ask for a find from G to D, and we discover that now these things were not connected before, but they are connected now. Okay, so I hope this gives some intuition between what we're trying to do. What does this UnionFind data structure supposed to solve? There's a comment about V times E plus V being some running time in the chat. I'm not exactly sure what that's referring to, but if that's referring to doing our breadth first search or depth first search for the entire graph, that should only be order of E plus V for the preprocessing. We shouldn't need to multiply by a factor of V to preprocess our graph, but maybe that refers to something else. Okay. There's another question. How is the union operation different from just adding edges between nodes? It's not. A union operation here is just adding edges between nodes, but you might imagine we want to do some extra work along the way so that when the find operation comes along, it's going to be a little faster. Okay. Is union A comma C redundant? It is redundant, it turns out. It is redundant, but it's an operation that we've done. I see a comment on how this relates to the maze pathfinding, and I will comment this really does not actually, does not relate to the problem set. You did not need this for any of this for the problem set. This is a different problem from that. This is not about shortest paths at all. Nothing I'm saying today is about shortest paths. Okay. So yeah. Okay, so here's what we have. We have these two operations, union and find. We have a transitivity property. If P is connected to Q and Q is connected to R, then P is connected to R. And we have essentially a bunch of connected components. So you can think of a connected component here as a maximal set of mutually connected objects. Okay, great. So one reason this is called union is because a lot of people think about these as sets, because like you said, it's sort of redundant to think of this as three separate edges, right? Thinking of A, B, B, C, and AC as three separate edges is sort of redundant. What's really going on here is we are maintaining three different sets of nodes here, right? That's what's actually going on. Okay, great. And if we do a union, if we union these two sets together, then we get one bigger set that looks like this. Okay, great. So disjoint set, UnionFind. This is the basic data structure. The interfaces supports two operations, a find operation that asks if two things are connected, if they're in the same set, and a union operation that unions the two sets together. Okay. Okay, so here's the plan. That's the problem, dynamic connectivity. I'm going to give you two very simple algorithms for it, and then we're going to talk about optimizations. Okay, that's our plan for the day. So to start off with, this is the quick find algorithm. You can guess what we are optimizing in this algorithm. So for the purpose of this algorithm, we're going to imagine we store our objects in an array. Okay, the array we have our list of objects. Here we go, and we have our list of our list of component identifiers here that say what each component is. Okay, great. Now, one thing we're going to do to simplify our lives a little bit is instead of thinking of these as components A, B, and C, we're going to name each component after one of the nodes in the component. So instead of calling them A, B, and C, for example, this component we're going to call 0 because item 0 is in it. This one we're going to call 1 because 1 is in it. And not that one. This one down here we're going to call 3 because 3 is in it. It won't always be, let me be clear, it won't always be the smallest element in the component that is the name of that component, but it might be. Okay, so to simplify, we're going to name each component after one of the items in the component. And two objects are connected if they have the same component identifier. Okay, so by the way, what if your items are not integers? Let's imagine that you were given a set of things that are not integers, set of real numbers or something. And you somehow want to use them as part of a UnionFind data structure. How do you think you might want to use these things? How might you convert these items into integers in a useful way for this type of array? Again, our goal is we want to be able to store the items, like this in an array. We'd like each object to have a name that we can store in an array like this. What do you think? This is sort of an aside, but we were talking earlier about how different things we've talked about connect together. This is one of them. And as I said earlier, quadratic probing is not one of the answers I gave you here. Not really. But there is one answer here that's related, and I'm going to go on in a sec now. In fact, you can use open addressing, right? So things like a hash function have collisions. So if we want to assign things to integers, we don't want collisions. We want everything to have a unique name. If you use chaining, you could use chaining to find a name for something. But what we really want is we want an array slot to put something in, right? We basically want an array slot between 0 and n for each of the items. And that's exactly what hash tables plus open addressing gives you. Couldn't you just enumerate them? Yes, you could also just enumerate them in some way, but you want some easy way to convert back and forth between the item and the name. Of course, you could use a hash table for that, but wait a sec, we're already using a hash table anyways. So either way, you might need some way to convert back and forth between the item and its name. Anyways, this is just sort of a random aside. Okay. I see a comment, hash table has collisions, didn't stop us in contest 2. Fascinating point. I was debating whether or not we should outlaw solutions with collisions or not. We didn't this year, but I'll have to think about that for next year. Moving onwards, though, quick find. So we have a set of objects. Where each object has a component ID that it's part of, and the component IDs are named after objects themselves. So now a find operation is quick. This is good. If I want to compare items P and Q, all I have to do is look at their 2 component IDs, compare component ID P and component ID Q. If they're equal, then they're the same component. If not, they're not. Easy, right? So the more interesting part, so here's our initial data structure. And now I want to do the union operation. This is the more interesting part, okay? So if I want to do a union of 2 items like this 4 and 1, I need to somehow go through and change the component identifier of 4 to point to a new component identifier of 1. Notice that initially everything is in its own component, right? Initially 4 is in 4, 1 is in 1, 6 is in 6, and so on. When I go through and I start doing the unions, I need to change 4 to be in component 1. Okay, how do you do that? There really is no particular magic here. You can just go through, enumerate all the items in your array, check if the ID is equal to the thing that you're updating, and if it is, then update it, right? So you're just going through, check everything, and update all the ones that need to be updated. Done. Okay, great. Here's another one. In this case, I'm connecting 4, 1, and 3. That means I'm changing 3 to 1. Good. Now I change these all to 2. Again, fine, and so on. Okay, so this is what union does. And let me now redraw this a different way. So we are drawing this like this as a connected graph. But there's actually a more convenient way to draw this. Instead of drawing it as a graph, I'd like to draw this as a tree. Okay, so I'd like to connect each item. I'd like to draw as the root the component ID. These are all in component ID 2. So let's draw 2 as the root, and let's draw everything as connecting to 2. Okay, I can draw it as a nice flat tree, and this just gives me an easier representation of what's going on. Okay, and when I merge 2 things together, so I merge 6 and 7, that's like making the parent of 6 equal to 7. And if I merge these 2 things together, then I'm going to take everything and make it all the child of 2. See, there we go. Everything is now the child of 2. Got it? Okay, this is just a different way of drawing the same thing. Okay, good. So given this, what do you think is the running time of the find and union operations that we have here? Let me give everyone a couple minutes to pop over to Archipelago and put in their answer. Okay, everyone put in an answer yet? Good, let's go on. So here it is order 1 for finds and order n for unions. This is why it is the quick find algorithm. Order 1 for finds, we already saw that. You're just comparing 2 component IDs. And see, here it is. This is just order 1 for finds and order n for unions, because you need to iterate through the entire array of all the items to find the things to union. Okay, so that is the quick find algorithm. Done. Let us move on. Let us talk about the quick union algorithm. Okay, so the problem we had before was we had these very flat trees. And having flat trees like this made the find algorithm very fast, okay? Because we just compared two things and we're done. Unfortunately, it made the union algorithm slow because we might have to update everything in a tree when we did a union operation. So let's say we don't care about having flat trees anymore. We're allowed to have deeper trees now. Okay. So in this case, let's imagine. Let's imagine we want deeper trees. So now I'm going to allow trees like this to form. Okay. So now in this case, 5, if you look at it, has a parent of 1, but 1 has a parent of 2, and 2 has a parent of 7, and 7 has a parent of 7. Okay. So if you redraw that as a tree, what you'll see is you now have a deeper tree of items. Okay. And because we're going to allow these deeper trees, it means that we don't have to do quite as much work updating parents when we do a union operation, right? On the other hand, it means that a find operation is now going to be more expensive. Okay. Notice, by the way, it's just one point. If an item has 7 as its own parent, that means that it's the root of the tree, right? That's kind of what that means as a signal that's going on here. Okay. So here's how the find operation works then. To do a find operation, we need to first iterate all the way up to the root. And once we find the root of the tree, we can then compare them. So for example, if I want to compare, the 0 and 1, how am I going to do that? I'm going to walk up the tree until I find the root. I'm going to walk up the tree until I find the root, and then I can compare them and decide if they are part of the same tree. So here's an illustration of that. First, I'm comparing 4 and 1. First, I walk up the tree from 4 to the parent 6, and then I discover that 6 is the root of a tree. Then I walk up from 1 to 2 to 7 to 7. I discover that 7 is the parent of a tree. Then I compare 6 and 7, and I say, alas, 6 does not equal 7. So the answer is false. 4 and 1 are not part of the same component. Okay. If they were part of the same component, they would have had the same root. Okay, great. So that's the find operation. That's going to be easy. How about the union operation? Well, the nice thing about the union operation now is that really all I have to do is take one tree and make its parent the other one. Okay, so I can just take, for example, 6 and point it over to 7, and then I'm done. That's the only thing the only update I have to make if I want to union two sets together. Okay, how does this work then? Well, if I want to union two sets together, comparing P and Q, okay, the first thing I need to do is I need to find the root of the P tree. So I walk up the P tree. I then need to find the root of the Q tree. So I walk up the Q tree, and then I can update the parents accordingly. Here's an illustration of that. Imagine I want to union these sets 1 and 4. So first I find the parents of the two trees. So 4 goes to 6, goes to 6, 6 is the root. 1 goes to 2, goes to 7, goes to 7, 7 is the root. And then I want to union them together. I point, for example, this 7 to this 6. I only have to update this one entry of the array, and it is all done. We have the final, we've updated our tree properly, and everything will work. Okay, so that is how the union operation works. Okay. Great. What was I drawing here? It's oh, this is after I've merged them. This is what you end up with. Now you only have 3 connected components. So here's just an example of how it works overall. I'm not going to go through this step by step, but I'll leave it in the slides for you to look at later if you want to see an example. Here I'm merging 3 and 4. 3 becomes the parent of 4. Here I'm merging 4 and 9. So 4 and 3 both become the child of 9. Here I am merging 8 and 0, so 8 becomes the child of 0. Here I'm merging 2 and 3. Where were 2 and 3? I guess here was 2, here was 3. So I'm just making 2 the root of 9. Okay. Here we go. Anyways, and it just keeps going and going until everything is happily unioned together and looks like this. Beautiful, right? As I said, I'm not going to go through this step by step, but I'll leave it in the slides for your later perusal. Okay, so that's the quick union operation. So let us try this again. What is now the running time of the find and the union operations? I will give everyone another 10 or 15 seconds to think about this and put in an answer. Last chance, going, gone. So the correct answer here is order n. Everything here costs order n because both the find and the union operations need to find the root, right? In order to do either of them, you need to find the root. Yes, perhaps you were deceived by the fact this was called the quick union algorithm, because on the one hand, it does do less work in part it does fewer updates to the union, but it still needs to find the root, and finding the root still involves walking up the entire tree. A surprising number of people guessed that the answer to this was order log n. In fact, order log n was the most popular answer. But unfortunately, nothing we have said yet gets us to order log n. Alas, I know that's what you want to hear. You want this to be an order log n algorithm, but it is not. And in particular, there's no particular reason you start out with 2 items and the union, well, puts it like that. Now I have another item and the union puts it like that. And another item and the union puts it like that. And another item, and the union puts it like that. Maybe you see the pattern at this point. After n unions, we have a tree of depth n. Okay, so n union operations, our tree is depth n. Each of the union and find operations now costs n. This is not very quick for find or union despite the name. Okay, so here for the find, we have to go to the parents. That's going to cost n. And the union, again, we have to go all the way up to the parents. That's also going to cost n. So both union and find are going to cost n. Okay, great. So here's where we are at so far. Quick find is slow because union is expensive. We have flat trees, and merging flat trees costs linear time and is expensive. Quick union is slow because the trees are too tall. They are unbalanced. Okay, and tall trees means that both union and find are expensive. Okay, so alas, neither of these is particularly good. The question is, can we do any better? Okay, that's where we come to, we've done this, we've done this, we've done this. Optimizations. I claim that with a few simple optimizations, we can come up with a much better algorithm. Okay, here's the first observation you might make. Let's imagine that you were implementing this algorithm, okay? And you were sitting here and you had to implement the union operation. And so far, we have said nothing about which way union does the merging. For this union, I can either merge this way, or I can merge this way, right? Nothing so far requires the union to go one way or the other, okay? So which would you prefer? Well, if you pause and think about it for only about 3 seconds, I suspect that you will do the union this way, that you will do the union in a way that gets you a shorter tree, right? Basically, you want to merge the shorter tree with fewer items into the bigger tree with more items, right? that's going to generally give you a smaller tree after your union operation. So let's do that. So that's what we're going to do. We're going to update our union operation to choose the direction of the unioning carefully. Right after you're done, if you do it the way on the left, you'll have a height 2 tree. This way you'll have a height 3 tree. Clearly, it's better to do the height 2 tree. Okay. Now, if you pause and think about this, the example I gave about trying to produce an n height tree doesn't work so well, because I start out with 2 items. I union them. Either way, it doesn't matter. But now I have a 3rd item, and I union them again. I'm not going to union them this way. That would be stupid. That gives you a deeper tree. I will clearly union them in a more efficient manner. I will clearly union them the other way around, not this way. Oop, I can't delete things properly here. I will clearly union them this way, right? Or no, sorry, that's whatever. Anyways, you get my point. Okay, so here's what we're going to do. We're going to maintain the size of each item. Okay, so for each item, we're going to maintain a size of that connected component. It's just one extra item to maintain for each item in our array. Okay, just like before, when we union 2 items, we are going to find the root of each tree. Okay, that's great. We find the root of each tree. Now we compare the sizes. If the size of P is bigger than the size of Q, then we're going to link Q to P. We'll set the parent of Q to P, and we'll update the sizes just by adding them together. Easy enough, right? On the other hand, if it's the other way around, then we link P to Q, and we again update the sizes. So one thing you'll notice is the sizes are very easy to maintain here, right? One reason that size is nice is because if I want to maintain the size of each subtree, I can very easily do it this way, simply by adding the 2 together. Okay, great. There's a comment that I'm missing a bracket. My apologies if I'm missing a bracket somewhere. Maybe here, maybe here. If that's the only typo you've seen so far in today's slides, then I'm doing amazingly well. So here we go. Here is an example of our weighted union. I now have 3 rows here in my array. I have the object ID. It's the size of the connected component, not even the size of the connected component, the size of the subtree rooted at that node, right? And then, so for example, let's look at item 4. 4 has size of 1 because this subtree is size 1, but 7 has size 4 because this subtree has size 4. So the size here is the size of the subtree of rooted at that node. Okay, great. I want to union 1 and 4, so the first thing I do is I walk up until I find the roots of the 2 trees. Here they are. 6 and 7 are our 2 roots. I then compare their sizes. I discover that 3 is less than 4. 3 is less than 4. Excellent, math works. And therefore, I direct the edge in this direction. Okay, there we go. And then I update the size of 7 to now be 1, 2, 3, 4, 5, 6, 7. Okay. That's how weighted union works. Let's see how it works in practice. Again, let me not go through this too slowly, but I'll leave it in the slides for you to look at later. But what I want you to see is that because we are now doing the union in the correct order, we're ending up with a much flatter looking tree. We're ending up with a much better looking tree. Okay, and here we go. When we're done, we discover that we have a nice tree that is not so deep. Okay, great. Just to compare, this is the version with weighted union. This is the version without weighted union. You'll notice this tree is much less nice looking, while this tree is better looking. Okay, great. What is the maximum depth of this tree? We don't have a lot of time, so I'm going to skip this question on archipelago. But if you think about it a little bit, we're going to see that the height of this tree is order log n. Okay, why is that? Let's see. So why do we get this height of log n? It's not at all obvious, which is one of the reasons I'm skipping this question, by the way. But let's see if we can figure out why that is. So let's imagine that I'm merging 2 elements. I'm merging T1 with T2. Okay. So I have two trees that I'm merging here. And the rule, of course, is again, I merge the smaller one into the bigger one. And so now let's just look at T1, focus on T1. And I want to ask, when does the depth of a node in T1 increase? So when does the cost of accessing a node in T1, when does a find on an operation on a node in T1, when does its cost increase? Well, if I merge T1 with something smaller than it, with something with fewer items, then whatever I merge it with is going to point to the root of T1, and nothing changes in T1. Okay, so if T1 has more elements, then nothing changes in T1, and nothing changes. Okay, so the only time that things get worse for T1, the only time the height is going to increase or the depth is going to increase for something in T1 is if the size of T2 is at least as large as the size of T1. If that's the case, we're going to put a link from T1 to T2, and everything in T1 gets one deeper in the tree. Okay, so that's the bad case. Let's see how often can that, so what happens here? Right, so here we go. It gets one deeper and its height goes to height plus 1. Okay, so here's the question is how often can that happen? Well, let's look at the size of the combined component. In this case, originally this component was size, whatever it was, size of T1. Okay, we know we merged it with something that's bigger than T1. And so we know that the resulting combined component is going to be at least size 2 times T1. Right? The size has to at least double. So this is the moral of the story. If the depth in T1 gets worse by 1, then the size doubles. Okay? So if worse by 1, then size doubles. Okay? Great. Let's look at that this way. So imagine you start off with T1 being size 1. There we go. And it gets merged with something that makes it worse. Stuff it gets merged with that makes it better, I don't care about. Stuff that's bigger than I don't care about. But eventually it gets merged with something bigger and it gets worse. Well, in that case, we now know it's doubled and the size of the combined components at least 2. Again, it might merge with smaller stuff, I don't care, but eventually it merges with something bigger and the whole component becomes size 4, and so on, until eventually the whole component is a size n. Okay? And so the question is, how many times can that happen? How many times can its size double before it gets to height log n? Okay. Well, before it gets to, how many times can its size double before it gets to size n? Well, the most number of times its size can double is log n times. Okay. So it doubles its size log n times and it's done. And so the biggest that a node, the largest depth possible for a node in T1 is going to be log n. Okay. Great. Again, I'm going to skip this in Archipelago. But now because our trees are all height order log n, the cost of find and union are both order log n, and everything works beautifully. And I should notice, by the way, that this technique we're seeing here of sort of doubling size at every time, this is actually a common technique you see in computer science data structures. So UnionFind is in some ways just a beautiful example of this paradigm you see a lot of making sure that you only do work, you only make life worse when things double in size. Okay, make sure that things don't get worse unless things get a lot bigger. And if you can do that, then you'll keep all the costs down to log n. So you see this paradigm a lot in more complicated, more advanced data structures. Okay, so here was our old weighted union algorithm. Here's our weighted union algorithm. It does what we just said. Where are we now? We now know that if we do, we now know that so quick find and quick union each have these order n costs. But if we do the weighted union, we do the unions in the right order, we get all the costs down to order log n. Okay, great. So far, so good. This was a very simple optimization. All we had to do was make sure we did the order of the union properly. There's one more optimization we can talk about, though, which is path compression. Okay, so here is a second optimization that you might do. After finding the root, we've done all this work to find the root. Let's make sure that we don't do that work again. So as I go along, let us set the parent of each traversed node to the root. So I want to take 10 and connect it to the root. I want to take 0 and connect it to the root. I want to take 6 and connect it to the root, 1, 2, and so on. Each of them I want to connect to the root. Here. Oh, sorry, wait. The find was not on 10. Oops, I ruined my example here. The find was on 11, or I don't know what I was doing here. Find seems to have been on 11, okay? So these are the things that I want to connect to the root. And here we go. Here in my example, I've connected 11 to the root, 6 to the root, 1 to the root, and 2 to the root. Okay, great. So this is nice. Basically, whenever we do an expensive find operation, we're going to compress the tree. if you think about this for a sec, you realize that from an amortized perspective, this should be great because we did a lot of work now to move everything up to the root. But once we've done that, in the future, all these operations are going to be cheaper because we've moved them all up in the tree. Okay, so in some sense, we're paying for our expensive operation by making all of our future operations cheaper. Okay, I see a comment saying I'm lost. So the point is, here was our find operation that looked at 11, 6, 1, 2, and 7. We started at 11 and we walked up the tree to the root. That was the find operation. While we did that, we took each item and we connected it back to the root. So we took 11, here we go, and we connected it directly to 7. We set its parent equal to 7. We took 6 and we set its parent directly equal to 7. We took 1, we set its parent directly equal to 7. We took 2, we set its parent directly equal to 7. So for every item that was on the path to the root, we set its parent directly to the root. Okay. Okay. So this was our old find root algorithm where we just walked up looking at the parent and the parent and the parent until we got to the root. If we want to do this path compression, we need to add a second phase here that goes back and walks the same path again. And while we walk the second path, the second pass through, we update every parent and point it to the root. Okay. There's a comment that says walk up and down. Actually, a common implementation of this, you only know what your parent pointer is, so you can't walk back down again. Right? Remember that you have this array that tells you who your parent is, but nothing else. But you can do the whole walk starting at the leaf twice. Okay. It turns out there's an alternate implementation where you don't even set things to the root. You just set each node to its grandparent, and that turns out to be good enough. And you can do that. In one pass, which is kind of an amazing alternative version of it, which turns out to be almost just as good. Okay. So there's a nice theorem from Tarjan from 1975. Tarjan, again, is one of the sort of foundational figures in algorithm analysis. And he proved this amazing theorem that says if you start from an empty UnionFind data structure, any sequence of m union and find operations on n objects takes n plus m times alpha time, where alpha is the inverse Ackermann function. And what's really nice about the inverse Ackermann function, it is not constant, but it will probably be less than or equal to 5 in this universe if the universe is anything like the size we think it is. In particular, 2 to the 65,533 would give us an inverse Ackermann function of 4. This is better than log star. I see a comment in the chat about log star. This is actually smaller than log star, the inverse Ackermann function. So this is the inverse Ackermann function is an amazing function. It is one of the slowest growing functions you can find. So it is a wonderful thing. If you take a computability class, there's wonderful, interesting things related to the Ackermann function. But that's not for today. So for today, we're talking about the inverse Ackermann function. And did I get anyone? No, we're not going to go through the proof of this. The proof of this is very difficult and requires some amount of well, more than we can do in the final 3 minutes of class. But the wonderful thing about this is, despite the fact that the proof is somewhat difficult, the algorithm is ridiculously simple to implement. Right? I mean, being able to, weighted union, easy. Path compression, really pretty easy to implement. This is a remarkably simple algorithm, and yet runs very fast again. Okay. There's another interesting question that any theorist would ask is, can we do better? Can we get a linear time algorithm for UnionFind? It turns out the answer is no. It turns out that Tarjan also proved that it's impossible to achieve linear time, which is also amazing. It turns out that this factor that grows super slowly is inherent to this problem. This is somehow an inherent part of this problem that you can't do it in linear time, which I find truly amazing. But again, unfortunately, we don't have time to do the lower bound proof in this class. Okay. Yes, no, Tarjan is, as I said, one of the foundational figures in algorithm analysis. Okay, so here's where we're at this point. Weighted union and path compression. Weighted union gets you down to order log n per operation, but you add in path compression, you get down to almost order 1, but not quite. You get down to this alpha m comma n term, which is a super fast data structure. Okay. Great. Someone often asks at this point, what about path compression without weighted union? I'll leave that for you to think about, but I have a few slides here trying to illustrate why with binomial trees, you will end up with order log n, even with just path compression, but no weighted union, you get order log n. I will leave that to you as an exercise if you are interested in it. Okay. Good. Going on, you might say there's another question that often comes up. What about union and split? What if I want to both be able to merge sets together and split them apart, right? Or effectively, you could say if I want to insert and delete edges and still ask about connectivity. This was a big open problem for a long time. It turned out to be a very, very hard problem. But it turns out that this was solved in the last 10 years. There's been a whole bunch of work on this problem. This was one of the key papers I've cited here, dynamic graph connectivity and polylog worst case time. And it's a wonderful problem and a wonderful sort of graph theoretic problem, how to implement union and split efficiently. Okay, you'll see this paper gets you log to the 4th time, and there have been improvements since then that get you down to, I think, log squared or something like that. I forget the most recent results on this. Okay. Okay, good. So I think that's all we have time for today. We have seen what I think are 2 beautiful data structures today, both based on trees. They're both ridiculously simple data structures to implement, right? A heap is just a couple lines of code. Just UnionFind also is just a couple lines of code, but they have some beautiful underlying structure to them, which I think makes them both amazing data structures. So this was your intermission, your break from graphs, and we will continue on Thursday and next week with graph problems again. I think that is it for today, and thank you.
Hi, Prof. I have a question regarding the path compression.
Yes.
Yeah, so previously you said like the amortized cost is low because like you did an expensive operation first and then subsequent operations are then cheaper, right?
Mm-hmm.
Yeah, so my understanding of amortized cost, right, is that if the first operation is an expensive operation, then the amortized cost for this will be high. But then like if I do like cheaper operations at the start and then I do a expensive operation at the end, then the whole amortized cost is considered smaller.
Yes.
Yeah, so I didn't quite understand
Absolutely.
with that.
So, well, so that was intuition, but you'll notice if you look at the actual theorem that Tarjan proved, it's that starting from an empty data structure, so meaning that each of the items is not connected to anything else, then any sequence of M union and find union and find operations takes this order n plus m alpha time. Right. So the point is that, so you're absolutely right that what I said was not a sufficient proof that the amortized time was good, right? It's that in fact, what's really paying for the cost is the fact that you already built up this deep tree. Somehow the process of building that deep tree is enough to pay for it. If you started out with your data structure already having a deep tree, then it would not have good amortized time, is maybe another way of putting it. So your observation is exactly correct.
I see. Thank you.
That help? Yep.
Hi, Prof. I'd like to ask for the union, right? What if instead of merging by size or weight, we merge by the height?
Mm-hmm. So you can do that. And you'll find implementations that do that. I think in general, people prefer using size because it tends to be simpler to update, especially when you are dealing with path compression. So you have to be careful because when you want to combine the weighted union or height-based union with path compression, I mean, I didn't talk about this when talking about path compression, but you don't want to have to go through and update too much stuff when you do the path compression, right? When I do the path compression, I don't want to have to go update the heights and the weights of lots of things. And so the nice thing about size, at least, is that it's relatively easy to keep the sizes good enough because the size of subtrees doesn't decrease. On the other hand, my guess is you can do similar things with height. I think in practice, people have found it just to be a little trickier to get right, but you certainly can.
Thanks.
Okay.
Hi, Prof.
Hey.
I want to ask about the path compression as well.
Yes.
When we do it, why is there no need to somehow update the weight? Like when you connect to the grandparent, right? The parent's weight would have changed, no?
Right, because you're only taking the union of roots of things.
Okay,
so what's important is that the weight at the root is correct.
Okay, makes sense.
Yep.
Okay.
As I said, this is exactly one of these subtleties that I just sort of skipped over, but that you don't want to go update the weight everywhere because that would be expensive. But luckily, you only merge roots, and so you only need to make sure the root weight is correct, and the root weight can never decrease, at least not as long as it's a root.
Okay.
And this is, again, why heights are a little more nasty to deal with, because the height of a tree can decrease when you merge things together. Even at the height of a root can decrease.
Makes sense. Okay, thanks.
Yep. Okay, if there aren't any more questions, then I'm going to call it a day. Last chance. Would the weight be more of a representation of max height? I mean, we've ended up showing that the max height is going to be log of the weight or log of the size. That's an implication of what we showed. We showed that, but aside from that, there's no necessity that low weight means low height and vice versa. But in this case, it is, because that's what you get from this merging the weights in the proper way. I'm not sure if that answers your question. I also see a question of, I don't get how this is better than the array version. I'm not sure exactly what that question is referring to or when it was asked. So I apologize if you reiterate. I'll try to explain. I'll try to give a better answer. I'll give an answer. The weight must be a function that increases monotonically. Yes. So in general, right? Weights will not decrease in the UnionFind. This is one of the reasons splits are a lot harder, of course, than unions, right? Splits can cause all sorts of weird things to happen, but in unions, the weight at a root only increases. Weights lower down in the tree can decrease due to path compression. Okay, last chance. Last chance, going, gone. Oh, there's the last question. What would the potential growth of breadth of tree? I'm not sure. I mean, in some sense, you can end up with a very flat tree when you're done, right? Due to path compression pushes everything up to the root, so you can pretty easily end up with a tree that's basically a completely flat tree. Yeah, unioning one by one, for example, will get you that. And I mean, even the example I had here, which was not very carefully chosen, gives you a fairly flat tree. All right. Okay. Okay, good. So have a nice week. See you.